Open the software by clicking on the Vibus new icon as shown on the screen. In this video, we will do load flow study. Mainly, load flow analysis gives the voltage at various buses under the given condition. It also calculates the power flow and power losses of all the branches in the given system. Therefore, load flow is used to investigate problems in power system operation and also planning. To perform the load flow, click on the load flow study icon as shown on the screen. This is a data entry form in the software. The configuration of the system where the load flow is to be done is shown at the bottom of this video. The branch data and transformer data entry are explained in detail in the Vibus formulation video. Now we want to enter the branch data excluding the transformer details. First of all, click on the enter branch data. Here 3 branches are there without the transformers. Enter all those details. First of all, click add row icon. So the from bus is 2, the to bus is 3, the resistance of the corresponding branch is 0.08 and reactance is 0.30. Similarly, the shunt admittance is 0.25. So enter the next branch, that is 2, 1, resistance 0.04, reactance 0.25, and similarly here also the y by 2 is 0.25, and the third branch is connected between 3 and 1. The resistance is 0.10, reactance is 0.35, and here there is no shunt admittance, therefore the value is entered as 0. Now we complete the readings for the branch data. After that we move to the transformer data entry. So enter transformer data, add row. The turns ratio connected to the 1 is ith bus, here it is 4 as shown in this figure. The jth bus is the point connected to the 1.05 turns ratio, that is 2, and R is 0 here, and per unit reactance of the transformer is 0.015, and Y by 2 is 0, A is 1.05 and B is 0. Similarly, the second transformer is connected between 5 and 3, and I and J are 5 and 3. R is again 0 here. The per unit reactance of the second transformer is 0.03. Y by 2 is 0. Here also the imaginary part of the turns ratio turn is 0, but the real part is 1.05. Now we complete all the data entry. So after that we move to the next, that is press enter bus detail icon to enter the bus details. While clicking this, based on the maximum number of buses as we enter here, for example in this case the maximum number of is 5, therefore a 5 row is created here numbering as 1 to 5. The default type is all are PQ. That is, the number of rows equal to the number of buses in the system is automatically appear on the screen. Our job is to select the type of buses and enter the associated data. Most of the textbook problems The bus details are specified. Here as shown the figure, bus 1 is a PQ bus where P generation and Q generation is absent or treated as 0 here. Also, P load and Q load are given as 1.6 per unit and 0.8 per unit. Therefore, P gen is 0, Q gen is 0, P load is 1.6, Q load is 0.8 per unit. In a PQ bus, the initial value of the voltage and angle is assumed as 1 per unit and 0 degree. Therefore, there is no changes made in these two entry. Similarly, moving to the second bus, P gen is 0, Q gen is 0 and P load is 2 per unit, Q load is 1 per unit. Here also 1 and 0 is the initial value of the voltage and the angle. Similarly, in the third bus also a PQ bus 0, 0. The entry is as shown the figure 3.7 per unit and 1.3 per unit 1 0. But indefinitely moving to the fourth bus, as shown the figure, bus 4 is a PV bus where P generation is equal to 5 per unit. But the Q generation and Q load is not specified because it is a PV bus. So treated this as 0. But P gen is 5, Q gen is 0, P load is, there is no load connected to this fourth bus, therefore P load is 0, Q load is, we understood it is 0. But the magnitude of the voltage is specified in the diagram as 1.05 and the angle is not specified, therefore we put it as 0. Similarly, and also one more thing, change the PQ bus to PV bus in this drop down menu. The last bus 5, the voltage and angle is specified in this figure. So this is a slack bus. At P, Q, both the generation and the load is treated here as 0. But the V is specified, it is in the figure 1.05 and the angle is also specified 0. We complete all the data entry here. Next is we move to the next page by clicking the load flow analysis icon. This is a result page. In this problem, base MVA is equal to 1. So no need to edit the value because default value itself is 1. But in the accuracy, the question specified we want an accuracy of 10 raised to minus 6. So tick here to edit the accuracy and put as 0.0001. So this is 10 raised to minus 6. And here no need of any acceleration factor is mentioned in the question. So a acceleration factor of 1 means there is no acceleration. So no need to edit this value. After that, click the Gauss seidel result. But the load flow is not converging here. So we want to check the data entry once more. What is the problem there? So click previous page. So we again come into the previous page, but here nothing wrong in the branch data entry. There is no error occurred here, and here also there is no more problem here. But here, yes, this is the problem here because it is slack bus, but here unfortunately we didn't put that. So again put the slack bus instead of PQ, the default PQ bus. Once again move to load flow analysis, go to the next page, change the accuracy to 10 raised to minus 6 and again click on the Gauss seidel result. The result tabulated in the screen are the voltage at all the buses in the system. The active and the reactive power flow are also tabulated as shown in the figure. The direction of the power flow is certain from the from and the to bus number. Also give the active power loss in megawatt and the reactive power loss in megawatt at various branches. The positive sign indicates the power loss or the absorption, and the negative sign indicates power generation. The result is validated with the help of textbook result as shown in the bottom of this video. To get the Newton-Raphson load flow result, click on the Newton-Raphson result button. The values are almost similar to both the cases, but some variation in the decimal place only can be seen in this table. To get more result, click on the next page. Here the fast decoupled result is also tabulated by clicking the fast decoupled result. To get the voltage, active power flow and losses, and the reactive power flow and losses at various branches are seen in the screen. The bar graph V of the voltage at all buses can be seen by clicking on the graph voltage at various bus button here. You can see the voltage at the various buses. The red color indicate the critical voltage bus and the green indicate the normal buses. The voltage are within the limits. Again, for more result, click on the next page. The number of iteration needed to achieve the desired accuracy corresponding to GS, that is Gauss seidel, NR Newton-Raphson, and fast decoupled can be generated by clicking on the number of iteration button. So here the accuracy is 10 raised to minus 6. The Gauss seidel takes around 175 iteration to achieve the desired value. Newton-Raphson takes only 5 number of iteration, and fast decoupled takes around 70 numbers of iteration to achieve the desired accuracy. The graph shows the error with respect to iteration corresponding to each load flow method can be visualized by clicking to this each button. This is the graph show error vs iteration corresponding to Gauss seidel, Newton-Raphson, and fast decoupled. You can zoom the corresponding graph to understand the convergence property of each method, where it is converged. All the details you can be assessed from this graph. Finally, to get a detailed report, the detailed report is generated by clicking on the generated report. Therefore, a report generated pop-up window is generated, and the report is found in the files where the parent file is situated. For example, here you can see the load flow file. When you open this file, the input details are shown in the first page, like branch details, transformer details, bus details, etc. And if you move to the second page, the detailed report corresponding to each method are given in page 2, Gauss seidel, page 3, Newton-Raphson, like voltage, active power flow losses, reactive power flow losses, and the fourth page, the fast decoupled, also are given in details. Moving to the next page, that is the fifth page, the comparison, the number of iteration, and you can also see the execution time, how fast it is executed. All these terms can be assessed from this page. You can also see the voltage profile, which is based on the Newton-Raphson method. Only one result can be seen here based on the Newton-Raphson method, along with the Gauss seidel error vs iteration. And the last page you can see show the graph of Newton-Raphson and the fast decoupled load flow error vs iteration. Thank you for watching.